Today's lesson, 10.8, is really a continuation of yesterday's 10.7. It's more examples of solving these polynomial equations. I want to look at example 6, which is another example of the factor by grouping that we looked at yesterday. I left example 5 there so to refresh you from yesterday. Again, 4 terms, no GCF. So I'm going to group those two together. The first group has a GCF of x squared. When factored out, will leave you x minus 5. Again, this one starts with a negative, so the negative has to be pulled out, but it also has a GCF of 5 this time. When you divide these terms by negative 5, the parentheses are going to become x minus 5. And just like we talked about yesterday, if you do that, this one and this one have to match. Now, to group them, you take the ones that came to the outside, the GCFs, they go in one group. And then what was left, or what was in common, go in the second group. And then that's what you set equal to 0. When I tee this up, this side would be x squared minus 5 equals 0. It doesn't factor. I'm going to do the square root method. Square root, so x equals plus or minus radical 5. This one would just be x equals 5. So I got 3 answers. I got x equals radical 5, x equals negative radical 5, and x equals regular 5. I knew I should get up to 3 roots because the highest exponent here was 3, which means it's to the 3rd degree. I got 3 answers and each one showed up once, so the multiplicity of all of these, is 1. So because each one showed up once, the multiplicity is 1. All right, let's try a couple more examples. On example 8, first of all, let's get it set equal to 0. So let's bring the 48x cubed over to the left side. When we look for a GCF, we can take out a 3x cubed. That will leave us x squared minus 16 equals 0. And inside the parentheses, we have the difference of 2 perfect squares. So the 3x cubed comes down. X squared minus 4 gets factored to x plus 4 and x minus 4. When we tee it up, this side's going to be 3x cubed equals 0. Which means x cubed equals 0. And when I take the cubed root of each side, I still get 0. But because this happened 3 times, it was x to the 3rd, the multiplicity of this is 3. On this one, x equals negative 4. That happened once, so the multiplicity is 1. And x equals 4 also happened only once, so the multiplicity there is also 1. In example 9, we have a trinomial again, so we're not going to have to worry about factor by grouping. We do need to find a way to break up the x to the 4th. I would start with x squared and x squared. This tells me the signs are the same. They're both negative, so minus, minus. And factors of 9 that add up to 10 are 9 and 1. So you could refactor these, or factor x squared minus 9 and x squared minus 1. They're difference of perfect squares. I'm going to do the square root method. So x squared minus 9 equals 0, x squared equals 9. When I take the square root of each side, I get x equals plus or minus 3. On this side, x squared minus 1 equals 0, x squared equals 1, x equals plus or minus the square root of 1, which is 1. Now, so my answers are plus or minus 3 and plus or minus 1. Because these each showed up just one time, they each have a multiplicity of 1. Now, on number 10, you have 4 terms again. When you have 4 terms, you want to think about factor by grouping. So I'm going to group the first 2 together, and I'm going to group the second 2 terms together. Again, in the first 2 terms, my GCF is 2x squared. That leaves me x minus 3. Here, I don't have a GCF, but remember, I have to take out the negative as -1, and that will also leave me x minus 3. The GCFs that you pulled out from the first factor, the repeated ones form the second factor, and then we tee it up. On this side, I'm going to have 2x squared minus 1 equals 0, which makes 2x squared equal to 1. Divide both sides by 2, so x squared is a half. If I take the square root, 1/2 is not a perfect square, so my answer is just going to be plus or minus 1 over radical 2. On this side, x is going to equal 3. And again, my roots are, so the roots end up being plus or minus 1 over radical 2. If you wanted to rationalize those, you could. It would be radical 2 over 2, and x equals 3. Because we have one that's plus and one that's minus 1 over radical 2, and then x equals 3, we have 3 real roots, but because each one only shows up one time, each one of those has a multiplicity of 1. You should try the remaining questions. The answer key is on Schoology, so try the rest, check your answers against Schoology.